Welcome to Study Loop.
Carnot heat engine uses a hot reservoir consisting of a large amount of boiling water and a cold reservoir consisting of a large tub of ice and water. In 5 minutes of operation, the heat rejected melts 0.04 kilograms of ice. During this time, how much work is performed by the engine? All right, first of all, so we need to kind of get the wording of this problem in terms of variables we can kind of plug into our model for heat engines. So first is if one reservoir is boiling water, and then it's at 100 degrees C, which is the boiling point of water. And if you have what does it say? Frozen, a large tub of ice. Okay, so if you have water and ice coexisting, that has to be also 0 degrees C. And so I wrote those down, converted them to Kelvin, 373 and 273, because I anticipated needing to use Kelvin in the problem. Wrote T is 5 minutes, although spoiler alert, we don't actually use that. And the mass of the ice for 0.04 kilograms, and we need to figure out how much work this engine's doing. Okay, so I actually got a little confused when I first did this, but I sort of figured it out, and I'm just gonna draw a little diagram to help articulate what I'm thinking. So here's our engine. You have the hot reservoir. It's got heat. It's a heat engine, not a refrigerator. So you can draw this picture like this. So heat goes in, work goes out, and heat leaves the engine. So we want to use this QC to melt the ice, and I originally made the mistake and said it was QH, but it should actually just be QC. So we want to melt this ice. So first, let's figure out how much heat is needed to melt the ice and set it equal to QC. So what were we trying to do? We are trying to, just simply melt the ice. So the heat is going to be simply to get it to undergo the phase transition of melting. It's just the mass of the ice times LF. Oops. And LF I meant to put in the box, but I guess it'll hang out outside the box. And then that's 3.34 times 10 to the 5 joules per Kelvin, just something you need to look up. The latent heat diffusion of melting ice. Great. So if you take M, which is 0.04, and multiply it by LF, which is 3.34 10 to the 5, then you get QC. And that's 13.36 times 10 cubed. Okay, now we have QC. Our goal is to get work. We can kind of just use the standard heat equations. So kind of take your pick. The first one comes to mind is work is E times QH. And let me just double check. This is a Carnot. Okay. Yeah, so it is a Carnot engine, so we have even more equations to use. We can obviously relate them to temperature. But so we can, and for efficiency, we can write 1 minus TC over TH. Like I said, because it's Carnot. And we want to multiply this by QH, but we don't have QH, we have QC. But again, for Carnot, we get another equation. So I'll kind of just do this on the side. So you want to do QC equals QH TC over TH. And then I'll just note because it's Carnot. Not always true. Only in the case of Carnot. Great. So then I'm just going to algebraically simplify this. So 1 minus TC over TH. And that means QH is equal to T hot over T cold times QC. And if you kind of distribute that to do some simplification, you get T hot over T cold minus 1 times QC. So if you take that and plug it into a calculator, maybe you'll get what I got, which is, oh, did I like not write down the answer? Okay, I think it's, let me double check on the exponent. So I think 4.89, and I believe it's times 10 to the fifth. Actually, let me double check. Okay, yeah, times 10 cubed. Ooh, that's a bad 3. Okay, yeah, and then the TH is the 373, TC is 273, QC is what we calculated kind of in step 1. And then actually, I'll just go ahead and number this as step 2. So that's your QC. And I'll just draw an arrow just to really like bring the point home that you put that there.